Awesome. Thank you so much for the invite, and it's been really great listening to the talks, especially because I've done a bits and pieces of most of them. It's really nice to see where the field has been going, and they're all relatively so novel, and it's really fun to go through all of them and the demos as well. So thank you for that. Coming to my talk, I'm Soumya Snigdha Kundu. I just started my second year today as a part of my PhD. At King's College London, supervised by Tom Brockoutryn and Jonathan Shapey. And my thesis has been recently going in the direction of semantic segmentation. And I'm personally interested in how you specifically tackle instance imbalance. In general, a lot of papers cover class imbalance, but here today we'll be talking about instance imbalance. And for the data I've worked on till now, I'll be mostly on the binary sense. I'm pretty sure as we go, you'll have a couple of questions, but please remember that the problem we're tackling here is still semantic segmentation. We might be talking about instances, but we're still, from the task perspective, on semantic segmentation, and that'll be important as we go through the talk. So we'll be discussing what exactly instance imbalance is and what is the issue with dice scores, which is something very common in segmentation. Moving forward, we'll go through how we can mitigate these issues on dice score, discuss losses from the perspective of how we match the metrics, and then just some results and analysis. So, what is the problem with dice score? The basic thing is that when you have multiple instances and you're doing semantic segmentation, where technically all instances are equal, you have the issue of if the dice gets biased to the larger instance. If you see on the bottom figure, in the case of where there is the three smaller instances and one large instance, if the large instance is missing bits and pieces and the other three are full, it's an 82 die score. But if that changes, it becomes a 95 die score for essentially the same number of misclassified pixels. And that's basically the issue with dice, where the way the metric is developed, it's very biased towards larger instances from the metric perspective, not the loss, as we will see later, but just from the metric. And this is some in-house data which we have, and we see that in particular to the brain metastasis, which is what I'm working with. Brain metastasis is a type of tumor where you have multiple instances of that tumor, unlike something like glioma or, as you saw with the meningioma, which is not very common where you have multiple instances. And you can see they're quite small and large compared. So there are multiple instances, and there's a very big differentiation in terms of the instance imbalance as well. So I'll be talking about brain tumor segmentation, automated brain tumor segmentation as a case study. Uh, Going back, I think we all know why automated brain tumor segmentation is important, but I think the main importance lies is when you're intra-op or you're going between cases from follow checkups. I think it saves a lot of time for the hospitals if you can automatically annotate the brain tumors. In general, for something like metastasis, when there are multiple occurrences, it sometimes takes like half an hour for a few clinicians to delineate the entire volume. So we'll start off from the metrics perspective as to where this problem essentially stemmed from. Because if anyone's following the field, you'll know that semantic segmentation models in brain tumor segmentation, they do quite well. It's on 85 for gliomas. Generally, like the Bratz challenges, they even touch 90. So you might be asking, like, is there really some scope? And now we'll see why there is when you tackle instance imbalance specifically. So what we want to do is basically penalize the models that miss lesions altogether, which is not really finely ingrained into the DICE metric, or for the loss, as we'll see, and then penalize the models if they bring up like smaller false positive lesions. And then, as we saw, that the large structure dominates the score as well. So we basically wanted to come up with a solution to all of them. And how can this happen? So we the first people to come up with this was the Bratz team, and what they basically found inspiration was like a bit of panoptic segmentation and instance segmentation metrics, where you match your predictions to the ground truth, and that's how panoptic quality as a metric came up. And this is what's been interesting as to how you can play around with the task and bring up ideas from different tasks into, from like panoptic and instant segmentation ideas into semantic segmentation itself. So as you can see, this is the case we'll be going with. There are four instances of predictions, three instances of ground truth, and the panoptic quality formula over here. If you notice, for the segmentation quality on the numerator, what you see is the intersection of a union over the specific instances. Just keep in mind this formula where the TP, the FP, and everything over here, they're all over instances, not pixels. So this is where I'm trying to differentiate between how semantic segmentation is formalized and how instant segmentation is formalized. Because in instant segmentation, you're worried about the group of classes or the group of instances, whereas in semantic segmentation, it's a lot more about the pixel level annotation. But just to get the instances into consideration into a semantic task, we're going to deal with the instances in the semantic formulation itself. So panoptic quality was the first matching scheme, and what they basically came up with was a one-to-one matching scheme. And what they do is, if there are multiple instances matching one ground truth, they take the best prediction and do not and considers anything matched as not a false positive. So as you can see here, this is how the matching would take place in panoptic quality. What the Bratz team came up with was a many prediction to one matching, so like a many to one matching formula. And you can see here is that what they basically came up with is, if there's any ground truth matching the prediction, assign them, and then calculate the dice for those specific ground truths. And you would see here is that one prediction is getting matched to two ground truths, which may be fine in terms of the overall calculation and how you want to frame it, but there's also the criteria of, do you really want to do that? Is that clinically relevant? So what we came up with was that, why not cluster them together, and only, instead of mapping them by just the ground truth, you cluster them and then consider the cluster as a whole and then do the dice over there. In this way, you can see that even though there's a bottom cluster over here, that would be equally weight to the entire cluster over there. And then we don't do any wrong mismatching. We have only one matching per ground truth or per prediction, and everything is, it's a new perspective where we solve a couple of challenges. And what these basically are is, all the three do solve the inflated score problem, which is, since you take the average between all the matching, you treat every instance equally. But the main issue comes in is where, what if you want to match two ground truths to one prediction? And you would ask me, why would I want to do this? You can just throw away one ground truth, but then you're penalizing the model falsely, or being extra, like you're being extra strict to the model, which might not be the best way to evaluate your scores, or it might show the wrong conclusion. Like, your model might be doing really well, but because of the way you're assigning your metrics, you're assigning your matching, it seems to do that your model is doing really bad. Like in this case, if you use the Bratz concept, which is the lesion-wise dice, you're scoring only 24, but with a different perspective to matching, you can actually score 43. Um, what I really want to mention here is that we're giving, our objective here was to let people, or let clinicians have an opportunity, or give them the ability to use different matching styles. You might want to penalize it really hard, or you might not want to penalize it. And the last thing is, what our main motive is, now going back to the whole idea of instances versus pixels, we're still on the pixel level. And if you see that in all of these matching criterias, you're always misassigning pixels. So through our case, if a pixel is actually a false positive, it remains a false positive. It doesn't suddenly become a true positive, and vice versa. And that's what figure four, and that's why I chose this explanation specifically, is that you're not misassigning pixels in any form. The most, I think this is a very common case where one prediction covers multiple instances, which in sometimes in the brain meds, you can have multiple instances close to each other, and your model might evaluate it in this way. So here you have like four actually quite drastic values depending on what type of matching scheme you use. So this is where we really want to showcase that you might be, it's not that you're evaluating the wrong way, but there's so many ways to evaluate, we can get these intuitions. You might want to consider a model which is good, like you might want this to be a good prediction, or you also might want this to be a bad prediction. And now we're allowing this choice, we're giving you this choice, which I think is quite important from the clinical perspective, or even interpreting your results from your model. We spoke about the metrics, and now, in general, in machine learning, I think most pilot studies are formed in a way that you're trying to optimize to your metric. And what I mean by that is, dice metric is basically the standard of what you're trying to evaluate in semantic segmentation, and you use the dice loss in general. Yes, you do use dice plus CE now because you want to stabilize dice, but essentially the whole concept is that you want to use dice loss, so you're optimizing to your dice metric. So we tried to do an ablation, and we chose like very basic losses, Tversky, dice, cost entropy, and then the compound losses like dice plus C in a recent paper really showed that using compound losses is the way to go for semantic segmentation. So we considered all those. But off late, there were two papers which came out. On the left is one of my supervisor's previous papers, and we wanted to think about, if you're optimizing for normal dice using dice, why can't we optimize to instance dice? So this instance form of dices through instance type of loss. And that's where this whole blob loss framework comes in, where you're trying to average the loss or take the mean of the losses across the ground truth of each component. And that's what really is the notion here, is that we're averaging through instances, and whatever the merits we're seeing in matching the dice is now faced by the loss as well. The other paper which I'm showing to my right is, it's actually a very recent paper, and what they basically prove here is that dice metric has, as we discussed, a bias to larger instances, but the dice loss has a bias towards smaller structures. So that's actually very interesting, because generally you want the metric and the loss to be the same, but here we see that the stark opposite. They also had another really interesting finding where, like, dice is preferring smaller instances, and they're biased to the size of the uh, they're biased to the size of the instance, but in case of cross entropy, they're more biased to the proportions of the instance. So they very neatly solve it by taking the L1 between the region sizes. And what they basically say is that the paper's name actually is, do we really need dice? And they get really nice scores and across like basic standard benchmarking tests. And so we came up with, like, obviously we now make our own compound losses, and then we do the matching based on the Bratz dice, our own proposed cluster dice, and obviously the normal dice as well. Uh, just before we go into the results, there has been some previous work on this. So there's been a very simple Mikai paper called, like, they basically propose loss reweighing, and what that essentially is that if you're giving lesser importance to the larger instances, they're giving more importance to the smaller instances. And this does work in class imbalance a lot, where you try to oversample, undersample, whatever technique you do, and they have good results for their paper, but the blob loss paper compares with them, and the second paper I'm going to discuss compares with them, and they generally say that this method does not work. So we chose not to experiment with it, but this has been something which has been proposed, I think, 2018. And in the second is this paper which came out again recently, tries to deal with the losses from the center perspective, from the boundary perspective, and they get nice results, but they ultimately get their best results by combining these new instance based, well, loss techniques into the blob loss framework. So that's how we stuck to the blob loss framework and didn't try to reproduce these results by them, but that's obviously something I plan to do down the line. Yeah, so going to the results, this is my experimentation setting. We take the baseline NN unit, three folds. We take the training cases only of the Bratz data set. And this is, I think, a very important metric which you want to highlight, is that there's 103 lesions of 10 millimeter, but increasingly the sizes go down, the number of lesions increase. And we did checkpointing not based on the normal die score, but on the cluster die score. and as usual, we just do it for 1000 epochs as the baseline setting. And you can see is that there's actually a very high dice score, like I mentioned, like 80, well, zero point 0.8 dice score. But you can see that the cluster dice score and the Bratz dice score, the lesion-wise dice score, is way lesser, around 55. So this gives the first motivation to pursue this problem is that when you're evaluating from a different perspective, which may be right or wrong, but when you're evaluating from a different perspective, there's a drastic change in the overall score of the models itself. Secondly, yeah, so you can see that on average these are like around 80, but here it's around 56. Now, the second important finding we saw was that RCE over here, if you look into the tables, is what is the new variant of cross entropy which they proposed. And they seem to do almost the worst in both the median and average scores. And this is what brings me to, like, this is my hypothesis. I mean, there's no way to validate it apart from the empirical standpoint, because even if you highlight the features from the segmentation map, it's not really in correlation to how you see it from a class activation map for classification. But just by seeing these scores, what I denounce is that only using the region cross entropy, where it's only being solving the bias to the proportions, you're leaving out what is essentially the ability to detect these small structures, and that's why it performs so poorly. So you can, something which may do really well for larger structures may not do well for smaller structures. And this is not something like, this is not, obviously it's not new or it's not highly novel. Like if you look into the COCO test sets, you generally have small, medium, large. So I think it's more of a an impact statement for the semantic segmentation community to look that, yeah, your model might be doing well, but it's only doing well on dice, or it's only doing well on larger instances, only for that class. So it's very important to look into newer benchmarking and newer ablations which you want to conduct. And because of that, the Bratz team from last year have included the lesion-wise dice into their well, benchmark scores and analysis. This is just the general distribution of all the scores. Just going back, you can see that. So what B Tversky CE means here is you take into consideration the blob loss. So which is basically the alpha global is just the normal loss, and then beta blob is taking into consideration the average of the weights. So we have a 2:1. Alpha is generally 2 in our setting, and beta is 1, and that's basically the combination. So in our case over here, we do the beta Tversky, so that's the blob part, and CE is to stabilize the blob version, and that gets the best score. What's also interesting here is that I think there's a nice way to compare the scores in terms of there being a quite higher variation between the instance scores as opposed to the normal dice scores. So that's also quite nice to see this larger variation, as because one of the in the recent ununique paper, one of their qualms was that brain tumor segmentation, at least for the glioma, was not a good benchmark data set. But that just might mean that you're evaluating it from the wrong perspective. Another interesting finding was that depending on whether you rank based on dice or rank based on these instance metrics, it really changes which loss does better. So obviously, you can see that Tversky with top K is like 11th on the dice, but since it's penalizing the false positives a lot more, and false positives are more than false negatives in this case, because you're creating those smaller values very frequently, and when you're penalizing that again and again, that helps with these instance scores but not that much with dice scores. And that's basically what's interesting, is that not only do you have to change the way you want to evaluate, but you might also have to change the way you form your architectures when you're dealing with instance imbalance. Something might not work with class imbalance but might work with instance imbalance. And these are the final scores in terms of just the binning by weight. And you can see that there's almost 95% accuracy with greater than 10 millimeter lesions, which is a fantastic score, but it drops down to 40 when you do it below 5 millimeter lesions. Um, there's I forgot to cite it, but there's this another paper which does that for, I think, the Bratz 2023 dataset and their in-house UCSF dataset, and they had similar values where they're actually 100% overlap in the 10 millimeter lesions, but actually only 70% in their below 10 millimeter and below 5 millimeter. So yeah, I think the main motive of this work was just first letting the community know that there's a very big problem when you're trying to consider the smaller lesions. And it's nice to see that when you're framing your metrics and you're framing your framework to be instance, they definitely get higher scores than mismatching the frameworks, which is quite nice. Then instance loss supposition metrics is what I just discussed. We perform multiple matching schemes, so you get a different perspective based on how you want to match your instances. And then this is not obviously it's not this is just on one data set. I need to test it on more. The one issue is this whole instance imbalance problem is not that frequent. So I have to hunt for some more data sets. It's kind of prevalent in microscopy data, so that's the next type of modality I'm going to tackle. But it might just be that UNet is might not be the best solution for smaller instances. At least NN-UNet, what it does is for the baseline model is just a simple UNet. So you might need to add something to the UNet, might be a tension, might be the residual connections, or might be something completely different. So I think it's a food for thought to take away that UNet has been the best model for quite some time now, especially with NN-UNet for semantic segmentation tasks, and it still is, as you can see, for the larger lesions. But when you go down, when you go smaller, that really might not be the case. My next steps would be I'm going to run some more extra ablations, checkpoint differently, incorporate distance metrics. As you can imagine, I didn't talk about Hausdorff distance or ASSD, and then finally run a case by case analysis uh, on those specific cases where does dice do well, does instance dice do well, and just variation on those, and try to get a more holistic understanding of where exactly are these models failing or succeeding. Thank you.